Hi guys, welcome back. This is chapter 19 on chemical thermodynamics. Here we go. Make sure you have your guided notes, textbook, and a calculator. Here we go. What determines spontaneity? I know you should have read this particular section before you start, but I thought it might be a really good idea to touch up on some of this because it can get a little confusing. So the question is, what determines spontaneity? We've already discussed enthalpy. Now, if you don't remember enthalpy, that was in thermochemistry. So I do realize that many of you are weak in thermochemistry, so we'll definitely be retouching this up when you guys come to next class. But I don't think that right now is the time to be reviewing this. So if you need to remember enthalpy, look back. All right, here we go. So we've already discussed enthalpy. That enthalpy alone cannot determine whether a certain reaction will proceed spontaneously. So it says there's something else we must consider. The change in randomness or disorder. Okay? That is technically what we call entropy. Entropy is the randomness or disorder in a quantitative number, which seems really weird. So it says spontaneous reactions and changes. It says it is inherent to us that when you put water in a freezer, the water will change to ice. And it says when you touch a hot burner on the stove, you'll get burnt. For both of these, energy is conserved. It must be conserved. But they occur without any outside intervention. That means they're spontaneous. No work necessarily was done to make your hand burn, except for the work from the heat that was on the burner already. It says spontaneous reactions. They have definite direction. They only proceed in one direction. It says exactly like when you drop an egg, it's going to break. That is spontaneous. It would be really creepy and weird if that broken egg suddenly came back together and was perfect again. That would not be spontaneous. That would just be creepy. So spontaneous reactions, they definitely proceed in one direction. They do not proceed in the opposite direction. So temperature and spontaneity definitely has something to do with this. It says temperature definitely has to do with spontaneity. It says at sub-zero temps, water will freeze. And it says we could spontaneously change that frozen water to liquid water if the temperature was above zero. It says the same is true for certain chemical reactions. So now let's check out sample exercise 19.1. Here we go. This is for you guys on the bottom of page 803. It says predict whether the following processes are spontaneous as described, spontaneous in the reverse direction, or in equilibrium. In other words, it's not going to proceed in either way. It will stay exactly as it is. And so here we go. Part A. When a piece of metal heated to 150 degrees Celsius is added to water at 40 degrees Celsius, the water gets hotter. So the question is whether or not that is spontaneous. I would think that that should be spontaneous. It says whenever two objects at different temperatures are brought into contact, heat is transferred from the hotter one to the colder one. That is like a thermodynamic law. It says thus, heat is transferred from the hot metal to the cooler water. And the final temperature after the metal and water achieve the same temperature, in other words, thermal equilibrium, there's no temperature changes anymore. I'm pretty sure that the water should be slightly hotter than it originally was, right? Remember, energy is conserved. Part B. Water at room temperature decomposes into hydrogen and oxygen gas. Man, wouldn't that be creepy if that actually happened spontaneously on its own? Don't you usually have to push a current through the water to make it decompose into hydrogen and oxygen? Man, that's not spontaneous. That's actually kind of creepy. It says, experience tells us that this process is not spontaneous. We certainly have never seen hydrogen and oxygen gas spontaneously bubble out of water. Okay? So that is definitely not spontaneous. It says rather, the reverse process, the reaction of hydrogen and oxygen to form water, that one's definitely spontaneous. So sometimes the reverse, you got to remember, that's what they want you to do, is think about the reverse direction. Hydrogen and oxygen definitely will spontaneously react with one another to form water. Okay, part C. Benzene vapor, C6H6, at a pressure of 1 atmosphere, condenses to liquid benzene at the normal boiling point of benzene, which is 80.1 degrees Celsius. All right, let's think about this. Basically, you're taking a gas, and you have it at a specific pressure of 1 atmosphere, and it says it condenses to liquid benzene at its normal boiling point. So think about boiling. The opposite of boiling is condensation. So they're condensing this liquid at 1 atmosphere at its normal boiling point. Everything sounds up and up to snuff, but you got to remember, at the boiling point, technically there are 2 states of matter that are present at the boiling point. Like for example, when you heat up water and it reaches the boiling point of 100 degrees Celsius, does the entire quantity of water just suddenly, poof, turn into gas? I hope you understand that it does take a while for the entire sample to boil away into the gas phase. All right, so let's read what they say. Part C. By definition, the normal boiling point is the temperature at which a vapor at 1 atmosphere is in equilibrium with its liquid. So I do believe that I hope you understand that anytime you hit the boiling point, the freezing point, the melting point, the melting and the freezing point, they're basically the same thing. Anytime you hit those specific temperatures, that is an established equilibrium. Okay, sample exercise 19.1, done. Reversible versus non-reversible reactions. It says some reactions can be reversed by adding or taking away the same quantity of energy. So if you take, for example, ice to water and water to ice, that's the freezing point and the melting point. It says in a reversible process, a system is changed in such a way that the system and the surroundings can be restored to their original state by exactly reversing whatever process you did to make the change. So let's take a good look at this. Go to page 805. The third paragraph down on page 805, I'm actually going to read it. It says, now, consider another example, the expansion of an ideal gas at constant temperature. A constant temperature process such as this is said to be isothermal. To keep the example simple, consider the gas in the cylinder and piston arrangement shown below in figure 19.5. When the partition is removed, the gas expands spontaneously to fill the evacuated space. Because the gas is expanding into a vacuum with no external pressure, it does no pressure volume work on the surroundings. In other words, work is equal to 0. It says we can use the piston to compress the gas back to its original state, but the only way that we can do that is to actually push on the piston. It says, but doing so requires that the surroundings actually do work on the system. That is, reversing the process has produced a change in the surroundings as energy is used to do work on the system. The fact that the system and the surroundings are not both returned to their original condition indicates that this process is irreversible. So, now let's look what it says. Now, imagine a piston with a gas in it with a partition. If you remove the partition, the gas will fill the whole container spontaneously. But the only way to get it back to its original volume is to squeeze the gas back. That means the surroundings would have to actually do work, because the gas is not naturally on its own going to go back into that tiny little space it started from. So, here's the main point. Spontaneous processes are irreversible. They don't naturally go back. Think of the broken egg. You drop an egg, it's going to break. It will not spontaneously re-put itself back together unless the surroundings can do work on it. I'd probably have to go get some glue or something. So, Why does certain stuff happen spontaneously? This is where that entropy comes into play. The symbol is a capital S. It is the tendency for systems to become more random. The more random or disordered something is, the greater its entropy value. So entropy is a measure of randomness. It says, consider the melting of ice. So you start with solid ice and you end with liquid ice. The question is, which one do you think is more disorderly? Do you think the ice is more disorderly or the water is more disorderly? Here's the general formula for delta S. You always take the final situation, the final product, and you subtract the initial product. So, final would be liquid water. Initial would be your solid ice. So here's your question. Is delta S positive or negative? That's for your guided notes. Let's consider the next one. Dissolving of salts in water. As salt dissolves in water, the crystalline structure is broken down. That means that entropy would increase. However, when the ion dissolves, water will start to surround those ions, right? This actually makes water more orderly. In other words, water was free to swim and be random and do whatever it's want. But as soon as you stick an ion into water, the water will naturally surround it. That means that basically it's been called to duty. It has a job now. That means it's more orderly. And the entropy for the water technically decreases. So for the entire dissolving process, it says this disordering process are usually dominant. Usually. So even though the water is becoming more orderly, it can't outweigh the magnitude of the disorder of the salt actually dissolving. And so it says the overall effect is an increase in disorder. This is just FYI. This is a lovely little trick question that they love to put on your AP written portions. So I thought I'd throw this in for you. Let's talk about reversible states. Don't forget that Q, the symbol lowercase q, stands for heat. It says don't forget that heat in a reversible reaction is equal and opposite. It says for a process that occurs at constant temperature, let's look at this. Q reversible, so it's got to be a reversible process. Q reversible over T, that means at constant T, is equal to delta S, the randomness, the change in randomness. This is a very important equation to remember. And your book goes through a very detailed history of where this came from. Rudolf Clausius, a German physicist. Okay, so an example of a reversible reaction at constant temperature is the boiling and condensation of water and steam at 100 degrees Celsius. You remember how it basically what we're looking at is an equilibrium where the forward reaction is equal to the opposite of the reaction. So the forward and the reverse reaction are happening at basically the same rate. So when I said heat reversible, Q reversible, this is when you don't have a spontaneous reaction. Okay? This is an equilibrium. I want to make sure that's very clear. All right. So when you do have a reversible equation and you do have a reversible reaction, this formula is beautiful. Q reversible over T is equal to delta S. And remember, it has to be at constant temperature. And that makes sense because most equilibriums happen to be either endothermic or exothermic. So temperature, when you add temperature, remember, think of Le Chatelier's principle. When you add heat or when you change the temperature, you are going to push the equilibrium to the reactant side or to the product side, and it'll have to reestablish a new equilibrium. So temperature has to remain still and constant. You can't change it. All right, moving on. Let's talk a little bit about this whole water boiling little section. So I'm always concerned that students don't understand that technically there's an equilibrium at the boiling point and at the freezing point or melting point. So let's just make sure we all cover this. It says to calculate delta S vaporization, because remember that's a reversible reaction, of 1 mole of water, We must realize that for a reversible reaction, the amount of heat transferred to the system during this process, known as Q reversible, is the heat of vaporization. We call that delta H vap. It says for water, delta H of vaporization is 40.67 kilojoules per mole at 100 degrees Celsius, and that's 373 K. I'm going to take that out. Boop. All right, let's take a look at sample exercise 19.2. That is on the bottom of page 807. Okay, so here is your sample question. It says, the element mercury, Hg, is a silvery liquid at room temperature. The normal freezing point of mercury is negative 38.9 degrees Celsius, and its molar enthalpy of fusion is delta H fusion 2.29 kilojoules per mole. What is the entropy change for the system when 50 grams freezes at the normal freezing point? All right, very simple. You need to realize that delta H fusion is kilojoules per mole. So what do you think you're going to do with this 50 grams right here? Pretty simple. Change your mass to moles and realize that once you have moles, you just multiply by this number and you'll have your kilojoules right there. All right, so let's take a look. They took 50 grams, changed it to moles. 1 mole has a heat of fusion of 2.29 kilojoules per mole. And then they changed the kilojoules to joules back. The question that I have is, why is this negative 2.29 kilojoules? Well, you need to recognize something. You're going from a liquid to a solid. It is freezing. If something is freezing, did it gain heat or lose heat? It lost heat, correct? So even though the heat of fusion, they gave you a positive quantity here, you should be losing heat, losing energy to make this stuff freeze. So the quantity should be a negative. Do you remember how delta H negative means that heat was lost to the environment? That's what we're looking for. So it says we can use negative delta H fusion and the atomic weight to calculate your Q. And that's exactly what we did. And so it's negative 571 joules. So that right there is just your Q. Q, that's it. So in order to solve for delta S, right, entropy, you're going to have to remember that this is technically a reversible, balanced equilibrium type problem. So to solve for your delta S, it's very simple. You're going to take that heat, that Q value, and it was negative, and stick it over the temperature. They said that the temperature was at its normal freezing point, which is negative 38.9 degrees Celsius. You got to make sure you change your Celsius to Kelvin. And so that's where they got this number, 234.3. Divide it, solve, you get negative 2.44 joules per Kelvin. Okay? And since it has a negative entropy change, my question would be, would you think that this should be proceeding from, like, naturally? Is this what naturally should occur? Is this, in other words, spontaneous? It says check. The entropy change is negative because heat flows from the system, making Q negative. We all got that. It's leaving the system. We want energy to be removed so that it can freeze. It says the process we have used here can be used to calculate delta S for other isothermal phase changes, such as vaporization of a liquid at its boiling point. So these melting and boiling points and freezing points, they all can be used with this formula. This delta S is equal to Q reversible over T, over a constant T. All right, so sample exercise 2, done. All right, let's further define a little bit of your entropy. So delta S is called entropy, and here's a really weird thing to think about. The second law of thermodynamics. The second law of thermodynamics was explained on page 808. It says that the delta S of the universe is equal to the delta S of the system plus the delta S of the surroundings. So basically, the key idea of the first law of thermodynamics is that energy must be conserved in any process. If you can remember that, then you'll be set. It says here, thus the quantity of energy lost by a system equals the quantity gained by the surroundings. Like, energy must be conserved. You can't randomly make energy if it wasn't there to begin with. So we've got this exchange happening between a system and the surroundings, and so they must be equal and opposite. And it says here, for any reversible process, the delta S of the universe has to be equal to 0. In other words, there's no net change in the randomness of the universe. But it says for any non-reversible process, the delta S of the universe has to be greater than 0. Non-reversible, right? That means it can't go back. Think of the broken egg. It can't go back. So, it says unlike energy, entropy is not conserved. That's creepy. The delta S of the universe is technically always increasing. That's a scary thought. The universe is constantly becoming more random? Even if the entropy of the system goes down in a spontaneous reaction, in other words, the products are more orderly than the reactants, that means that the entropy of the universe must increase because it's going to have to do work to get that back to its original state. It says this means that the surroundings must become more random in order to do that, to get the system back to its original status. Kind of creepy, huh? So it says, scary thought, no process that produces order in a system can proceed without producing an equal or greater disorder in its surroundings. And just to make sure that you get this, it says if you clean your room, you must expel heat to the air molecules around you. That makes the universe around you more random, more entropic. That was one of the words I used a couple years ago. Okay, another way to change delta S. A reaction that leads to a decrease in the number of gaseous molecules usually will lead to a decrease in entropy. And I gave you a great example. We've got nitrogen monoxide, 2 of those, and 1 oxygen molecule. So technically there's 3 molecules on the reactant side and only 2 on the products. It says the entropy change for that reaction technically is negative because 3 molecules of gas react to form 2 molecules of gas. So it became less random, if that makes any sense. It says the formation of the new bonds in the products lessens the freedom of the movement that you originally had, which brings me to another point. There are many different types of motion. You've got translation motion. Now, in order to make this make sense, check out the top of page 810. You've got all these different types of motion. Translational motion, full motion in the form of actual movement. It says gases have more translation motion than liquids, liquids more than solids, so the overall motion, okay, freedom of motion. Vibrational motion. Yes, molecules do vibrate. So look at the examples here on the top of page 810. They gave you a water molecule. There are many different ways that water molecules can vibrate. The hydrogens can pump out. The hydrogens can squeeze in. Think of like the Thigh Master. Or they can pump in and out on opposite directions. That is all vibrational energy. The final one is rotation energy. Molecules can spin. Think of water. It can spin around. It says, please note, the more heat that you have, the more motion you have overall. So bonding and types of bonding, we'll come back to this obviously, but bonding and types of bonding will limit how much translational, vibrational, and rotational energy you have. Okay, now it's time for the final run on 19.3 and 19.4. Sample exercise 19.3 for you guys begins on page 814. Okay, so let's start doing sample exercise 19.3 on page 814. So here's the question. It says, predict whether delta S is positive or negative for each of the following processes, assuming each occurs at constant temperature. So the first thing that you have is you've got liquid water turning into gaseous water. So overall, guys, you just need to say, which one do you think is more random? Is liquid more random or is gas more random? It looks like you have 1 mole of each on each side, so that doesn't matter. Which one is more random? It seems that water, gas, would be more random, and they placed it on the product side. Remember this, overall delta S will be delta S final minus delta S initial. So your final state has more randomness. That means that your delta S has a higher value here than it does here. So this number will be small, this number will be large. It would appear that for part A, delta S is positive. Let me just triple check right there. Delta S is positive. Let's go to part B. You've got silver ions and chloride ions forming silver chloride solid. This really doesn't take very much guesswork. So basically in this process, you've got ions. Remember, ions are pretty much free to move. They're allowed to be in that. Water thinks they're dissolved, they're aqueous, they're in water. But then, all of a sudden, you take those ions that were originally free to move around and do as they please, and you form an ionic bond, silver chloride. Do you think that the establishment of this bond will make it more or less random? I hope you know that that will make them less random. So remember, it's always the products minus the reactants. So delta S final minus delta S initial. The final is much lower than your initial. So you have a low quantity minus a high quantity. I hope you realize that this makes delta S negative. Part C. Here you have 4 iron atoms and 3 oxygen molecules forming 2 iron oxides. For this one to make a little bit more sense, you got to think about total number of moles and the addition of bonds. Okay? And the book says the particles of a solid are confined to specific locations and have fewer ways to move. In other words, fewer microstates is the way the book calls that. Then do your molecules and your gas. Molecules of your gas. So it says because oxygen gas is converted into part of the solid product, delta S is negative, but really this should be common sense. You've restricted all of the atoms and molecules to be in a more confined state. It has been solidified. So delta S is less random than your initial is. Okay, initial is much more random. So you have the same thing right here. Your final is lower in randomness than your initial is, so it should be negative for part C. Part D, the last one. You got nitrogen gas, you got oxygen gas, and then you form nitrogen oxide. Don't be confused with this guy. This is a common misconception on students is part D. So let's make sure you understand what's happening. You have 2 molecules here. You've got 2 molecules here too. You've got nitrogen, you've got oxygen, but here you've got nitrogen oxide. So it has a little bit more to do than just the number of molecules. So we got to dig a little deeper on this guy. It says the number of moles of gases on the both sides of the equation are the same. And so the entropy change, like think entropy heat change, is going to be small. The sign of delta S is impossible to predict based on our discussion thus far. Trust me, we will get back to this when we talk about bonding and types of bonds. But we can predict that your delta S will be close to 0, but we can't confirm it until later. For now, trust me, it is close to 0. And we can explain whether it is a small, tiny little negative or a small, tiny little positive once we explore bonding. So for now, part D, mostly 0. Sample exercise 19.4 begins on page 815. It says predict which sample of matter has the higher entropy. So choose the sample of matter that has greater entropy in each pair and explain your choice. You have a choice here. 1 mole of sodium chloride in the solid, or 1 mole of hydrochloric gas at 25 degrees Celsius. For part A, pretty simple to explain. You have a gas versus a solid. There's not even a gamble here. It's pretty easy. Your HCl will have a higher entropy because gases, remember, have more rotation and vibration and translation. All of the 3 types of motion. And therefore, your HCl will have a higher entropy. Part B. You have a choice. 2 moles of your hydrochloric gas or 1 mole of your hydrochloric gas at 25 degrees Celsius. Again, a sample containing twice as much molecules as the other one, that's a no-brainer. The 2 mole sample has twice the number of microstates, twice the number of basically types of rotation, right? Even though they are at the same pressure, this should be a no-brainer too. Part C. 1 mole of HCl gas or 1 mole of argon at 298 K. They're both at the same temperature. One of them has got a bond. You've got a noble gas. Does this help at all? I hope it does. I hope you understand that the HCl sample is going to have a higher entropy because the HCl molecule is capable of storing energy in its bond versus argon. Argon has no bond. It's a noble gas. So molecules versus atoms, always shoot for the molecules because they form bonds, and bonds store energy, and they can have vibration energy. No brainer. Let's move on. After this comes the 3rd law of thermodynamics. It says if we could have a perfect crystalline structure. Now, if you're curious what a perfect crystalline structure would look like, look at the top of page 816. If we could have a perfect crystalline structure at absolute zero. Now remember, absolute zero, have we ever been able to reach absolute zero? No, but we've been very close. You'd have to have a perfect crystal in order to even think about approaching absolute zero. If you could approach absolute zero with a perfect crystal, it says then the entropy is randomness, of the system would be exactly 0. No randomness and perfect in every way. No vibrational energy at all. No rotational energy at all. Perfect in every way. So, entropy dramatically increases between the solid, liquid, and gas phases. So let's check this out and notice the temperatures here. Basically what you have is temperature down here, entropy reading over on the side. This is pretty much the same as the figure 19.4 on the bottom of page 816. So why do you have almost these perfect straight lines occurring twice? We're talking about water, basically. This is probably water. So entropy increases as the temperature of a crystalline solid is increased from absolute zero. Those vertical jumps in entropy will correspond with your phase changes. Do you guys remember Q reversible? For us, delta S is equal to Q reversible over a solid T. That's when the system is at equilibrium. So sometimes some students, when they see this, they're like, oh, hey, that makes sense. Anytime there's a vertical jump like this, the system must have been in an equilibrium state. A state at which you've got a change in entropy, but it's also concurrent with a change in state of matter. So it says why? At each physical change, your volume, think about this, the energy being added to the system isn't making the molecules move any faster. But guess what it is making those molecules do? Increase volume. Think about when a solid changes to a liquid. Think about when a liquid changes to a gas. You will continually have volume changes at each of those phase changes. And notice that there's a smaller jump when the solid changes to a liquid versus when the liquid changes to a gas. Look at the much bigger jump here. That is why you've got a huge amount of energy that has to be put into the system to change it from a liquid to a gas. In general, here are some things to remember about entropy. Your entropy will increase when liquids or solutions are formed from your solids. Your entropy will increase when gases are formed from either solids or liquids. And then finally, your entropy will always increase when the number of molecules of gas will increase during a chemical reaction. I'm done, guys. You have a great evening. Bye-bye.